So last time we talked about we talked about infinite sets. A set is denumerable if it is in one-to-one correspondence with the natural numbers. What does this mean? It means there exists a one-to-one function from the natural numbers into intervals 0 to 1. I'll call it f. Can anybody give an example of a one-to-one function? From the natural numbers into the interval from 0 to 1. What's it? Oh, yeah, there's a one-to-one function in that range. Yes.
N is 1 over n.
Okay, sure. So half of that.
Yes.
And I know why you went half, did you? Right? Because otherwise, if you didn't have that 2 there, then 1 goes to something that's not in there, right? Well, certainly this will work, right? This takes 1 to a half, 2 to a 4, 3 to a 6, and so this function is 1 to 1. By the way, it's certainly not onto, right? Because there's lots and lots of garbage in the interval from 0 to 1 that it misses, right? 0.9 is not in there, and pi over 86 is not in. There's all kinds of stuff that's not there. Now, this was the last big theorem. This technically means we part out in natural numbers is less than or equal to, because there's a one-to-one function from here to here. This thing is a stronger statement. It means there's a one-to-one function from here to here, but there's no function that's onto, so there's no bijection. So the last thing, this is a big, there doesn't exist a bijection. You might have think that you just, Jim's not very smart, maybe he just didn't think of the right map here, right? Because certainly we've missed a lot, but we could do something else and make it look a little tighter, right? Daniel, you went 1 over 2 in. Here's another way to do it. You can certainly do that. This, just like the previous one, takes 1 to 1/2, but now it takes 2 to 1/3 and 3 to 1/4. So this seems to get more fractions, although that's kind of not true. How do I know that somewhere in the depths of some Stephen King novel, there's not some function from here to here that actually covers all of 0 to 1? It can't be done. It cannot be done. Such bijection exists. I discussed this in last class, but this is a very important argument. It's called Cantor's diagonalization argument. I won't go into details of this. So we will say that suppose that we do have a bijection. So you input a natural number that outputs some number an between 0 and 1, and we're going to assume that we can cover everything, right? And we're going to get a contradiction. So if this works. Seeing that this function covers everything, that's the key thing. We've already shown that there's a one-to-one function. The tricky part is to cover it, right? Make sure that everything in the interval from 0 to 1 is covered. So to this end, let's write this as a decimal. Three, one, two, three. So all my decimals here, each AI, J, between 0 and 9, right? So I'm assuming these are just base 10 decimals, right? And also I'm gonna make a rule here. No ending in an infinite string of nines. This really doesn't matter here so much because this will be a function, but there are a couple of catching points. What's one problem? Why would you not want to end in an infinite string of nines here? What is the decimal number 0.999999 forever? It's 1, and 1 is not in the interval from 0 to 1, right? So, right? So that's one reason why I don't want to do this. Notice that every decimal is unique, can only be written one way unless it ends in an infinite string of nines or an infinite string of zeros, right? So for example, 0.5 can be written 0.49999. By the way, I'll let you use that on the next homework, that statement I just made. Prove it for me for extra credit. It's not too difficult to prove that in base 10, if you don't end in an infinite string of nines or an infinite string of zeros, then it's unique. Okay, so here's what we're going to do. If we assume that this function is onto, then every possible decimal is in this right column. Everybody agree with that? I'm going to build something new. I'm going to create the following number X, is between 0 and 1. I'm also going to write this as a decimal. And I am going to define Bn by looking at it this way. I'm going to let Bn be 1. My choice is become for somebody. So here's what I'm going to do. This is what way I'm going to build this decimal. I am going to look in my table here. How do I choose B1? Well, look at this, A11. I look at the first decimal and the first number. If that turns out to be a one, if that turns out to be a one, I'm gonna let B1 be 2. And if it turns out to not be 1, I'm gonna let it be 1. So any other thing, I'm gonna let it be 1. How do I choose B2, the second number? I look at this guy. If that one is not 1, I'll let it be 1. And if it is 1, I'll let it be 2. How do I choose the third one? By looking at that. So you see what I've made, I call X my contrary decimal. Because X disagrees with A1 in the first decimal, right? And it disagrees with A2 in the second decimal. And it disagrees with A3 in the third decimal. And in general, it differs from AN in the nth decimal. Everybody agree with that? Note B1 is not equal to A and N. Right? I made it so. So X is not equal to AN for any N. It can't be any of these. It disagrees in the appropriate decimal. And since I demanded that none of the decimals end in an infinite string of 9, decimal representations are unique. And so anything that disagrees, even in one place, has to be different. X is not in range. So cannot be on. This contradicts the fact that we assume that f is bijection. This is a big one. So there is a 1-to-1 map here, but no onto map. So this should maybe kind of interest you a bit, because what this means is both of these are infinite sets. I think we can all agree with that. The natural numbers is an infinite set that is smaller than the number of decimal expansions on the real line between 0 and 1. Okay. Any questions? Okay. The smallest kind of infinite set, it turns out, is going to be the size of the natural numbers. And remember, we call such a set an infinite set that's in 1-to-1 corresponds with the natural numbers denumerable. There are lots of denumerable sets, and in a certain sense, you can argue that this is really one of the most important types of infinity. It's the smallest one. The natural numbers are denumerable. The integers, rational numbers, the natural numbers cross themselves any finite number of times. These are all denumerable sets. What does it mean? The countable definition. Set S is said to be countable if S is finite or denumerable. I mean, I guess we want to call it finite, so it's countable because you can count them. And what it means to be denumerable is you can put it 1-to-1 corresponds in the natural numbers. So in other words, you can list it, right? Like a sequence. Remember how in Calc 2 you list sequences, A1, A2, A3, et cetera. Sequences are basically denumerable sets, subsets of the real numbers. Well, actually, the sequence could be constant, so I guess I should say it. Should be a countable subset of things. So said it was countable, it's finite, or it's denumerable. That's why so denumerable or denumerable means that you can list it even though it's infinite, right? So if I have a family of sets, this is a countable union. All right. But this is, what if my index set is real, right? So now I have a set for every real number. I can't put these kind of in order and list them like this, right? That's the problem. That's why sometimes people early on, I say, well, you want to use this notation here because you can't really list the reals the way you list the natural numbers. You can't go 1, 2. You can actually, and this is one thing that's kind of might mess with your intuition a little bit. We'll see this later. You can actually also list the rational numbers, even though there are no rational numbers that are exactly next to each other, because of the fact that the set, there is a function, there is a way to list the rational numbers. And we'll see that later. Let me start you off with a theorem that you probably are not going to find too surprising. Proposition. 532. If S is numerable, then how many of you have ever heard of the Hilbert Hotel? This is this is probably important math culturally, right? So my brother actually is a crazy hotel king, right? When he's out of rooms, he's out of rooms. This is why I would be better at hotels, my brother. I hope you're watching this on YouTube. So Hilbert's Hotel actually has one room for every natural number, room 1, room 2, forever. Now, suppose that Hilbert's doing great business and the hotel is full. And one more person, somebody really important, comes and you want to not turn this famous person away, right? So what do we do when the Hilbert Hotel is full? I mean, every room is occupied. What do you do?
There are there an infinite number of situations there were already infinite. So
All right, so here's what you do. You send like a little message to everybody's phone in the room and say, sorry for the inconvenience, but everybody look at your room number and move to the next higher room. Person 1 room moves to room 2, person room 2 rooms move 3, et cetera, et cetera. And now, guess what? Room 1 is unoccupied. And so now you can accommodate your famous person. But what if a whole bunch of famous people came? Right?
process.
What if infinitely many came?
Start the process.
Well, you'd have to repeat it infinitely often, so and also let's sort of discard the fact that you've got infinitely many people shuffling around, the hotel will probably collapse or something. But here's another way you could create infinitely many rooms. Now, you call everybody in the room and say, okay, now, instead of moving to the next room, move to the square of the room you're in. And if it's in my hometown, you provide them with a calculator, so you can figure it out. But that means that person one stays in their own room. Person two moves to room four, person three, room nine, person four, rooms. How many natural numbers are not squares? A lot, right? Infinitely many, right? So by doing that process, you've now created infinitely many new rooms. We're going to Hilbert Hotel this thing, right? Yes.
Always say this, all right? Why can't you just say like everybody would advise your rows and then you people think about it?
You could do that. You could certainly do that. I thought a square was more interesting because it creates bigger and bigger gaps. But yeah, so the point here is you could just tell everybody to move to the double of their room, right? And that will create, gaps. Yes.
If all the rooms are full, like, if all the, like, just from the first example, all the move over once, like, isn't the last person, like, they don't have a room, because all rooms are full, like, what?
There is no last person, and that's the point, right? This is part of the problem of counting the infinite, right? There is no last person. And also, there are mathematicians that think things like there are no infinite sets. I think this is a little, kind of crazy a little bit, because if they want to argue that there's no infinite sets, there's not infinitely many people to put in a hotel with infinitely many rooms, all that is true. Right? There aren't even an infinite number of subatomic particles in the universe, probably. However, there are people that argue that there is a largest natural number, and we will not be embracing that. So how do we do this? What it needs to be denumerable is I can put a one-to-one cardinality with natural numbers. So let me first point out if X is in S, then we're done. Because that means that S union X is S. Now I already know that this can be put in one-to-one. So, okay. So the interesting case is what happens when X is not in S. The maximum is S, the power. So this function from the natural numbers to S is one-to-one and onto. That's what it means for S to be denumerable. Now we're going to define from the natural numbers to S union X. Well, can anybody figure out how we might do this? Let's do it like our first hotel. Who's the new player here? The new player is X, right? So let's stick X in the first room. So room one goes to X. Okay. What should we do now? Well, whoever was originally, let's see. This. So. Two, whoever two is, goes to F of one. So the room originally occupied by one. Person three goes to the room originally occupied by person two, four goes to the room and so forth. Okay, so this is a function. Right. Right, because this is well defined, given any input, I know exactly what the output is and they're not doing, right? We need to argue that it's 1 to 1. Okay. Suppose G of n equals G of m. Let's break this down in cases, so it might be easier. Case one. Well, in this case, if one is what, X, right? And well, that's F of m minus one, correct? Is it possible for these two to equal? And why or why not? And what's wrong with that? Why can't X be F of m minus one?
X is in.
Because F of n minus one is in S, and this is a contradiction. So this case is eliminated. So by symmetry, you can't have one of these numbers being one and the other being bigger than one, right? What if n and m are both bigger than one? N equal P of m implies F of n minus one equals F of m minus. Great. Well, what do we know about F? That's right. So in particular, it's 1 to 1, right? So n equals m. And the last case is silly. And of course, it clearly works here because if they're both one, they're equal to each other. So this new function we built, this Hilbert hotel function, is still 1 to 1. And basically it hinges on the fact that F is 1, right? Number two, we need to know it's on. Okay. Let C B and S union X. Well, again, there's two cases to consider. Case one. Z equals X. Is this covered? Yes, it is. So X is covered. Case two. Z is not equal to X. So Z is in S. But this is a bijection. So there exists, let's say, K in the natural numbers such that F of K is equal to C. Notice that G of K plus one is equal to F of K, which is C. And so it's. There's a careful proof of the Hilbert Hotel. Let's generalize this. At first blush, this looks, and actually, I think we'll steal an idea from you on this. If A and B are denumerable, then so is the union of A and B. Position. Um, I'm gonna do, part of this is gonna depend on something we do a little bit later, but I think that this is, but this is actually, this is more serious than the previous one, right? Okay, so in the last one, I said, okay, if you've got a set that's denumerable and you throw one more in, it's still infinite and in one-to-one process, natural numbers. No surprises here. This is more serious, right? This is like if you have an infinite set that's denumerable and another infinite set, and you throw it all into a big pot, it's still just denumerable, right? By the way, this is very clear, isn't it? If A and B are the same set, right? Because then their union is just the original set. So this actually kind of, that observation gives me a hint about how much or how to proceed. Proof. And this is really the meat of it. After this, if I prove this step for you, I think it'll be, okay, it's clear why this is true, and the rest is kind of sweeping up details. Since A and B are enumerable, there exists functions, well, let me say bijections. I'll start. F from the natural numbers to A and G from the natural numbers to B. And I said it, but I didn't write it. So let me make a note here. Assume that A and B have nothing in common, right? I said, I'm going to assume you're disjoint. I didn't put it down. Define So. What are we gonna do? I'm gonna steal your idea about switching them off here. So I'll let you prove it in gory detail that perhaps it should be done. Let me show you how age works. Uh, this is really what this map is doing. It's sort of like shuffling a deck of cards or zipping up a zipper, right? That's kind of what's going on here. It takes the odd ones, F1, F2, F3 like this. And it takes the even ones like this. Everybody okay with that? Why did I assume disjoint for this case?
Something.
That's exactly right. That's exactly right. Let me point out that this function H automatically onto, right? Because take an element of A union B. What do I know about an element of A union B? It's either an A or it's an B. Well, if it's an A, it turns up as one of the yellow ones, right? And if it's an B, it turns up as one of the white ones down this. Everybody agree with that? So that is not a problem. We needed this to actually, I did say bijection, to show that it's 1-to-1, because if they've got stuff in common, this map won't be 1-to-1. Suppose, for example, the G of 1 is in A and B. So G of 1 appears also as, say, F of 3. Then all of a sudden, you've got two different inputs going to the same output, right? So we needed here sets to be disjoint for this to be 1-to-1. Let me point out that this map is onto, right? And so in a certain sense, this is smaller than the natural number, right? Because everything is covered from the natural number by this. It's all automatically onto. I'm gonna get into more of the details of that. Well, but so in the case that these are disjoint, this is the bijection that we wanted. In the case that it's not, here, A and B are not. Replace D with B minus intersection. Now, notice that A union B is equal to A union C. Everybody okay with that? Because this is just basically filling out the intersection. And C is countable. How do I know this? Because it's a subset of a denumerable set has to be countable. We haven't done that yet, and we're gonna see this later. This is probably fairly obvious to you that if you have a set that is in one-to-one correspondence with the natural numbers, then any subset of that is either finite or also in one-to-one correspondence with the natural numbers, right? It can't be any bigger than that. But we'll see this more formally later. And so, why does this work? Well, so for example, if they, right, if C is the empty set, for example, then that means that A and B are the same. Well, it means that, yeah, their intersection is B, say. Then you're left with only A, which we know is denumerable. If C is finite, then you can use the previous theorem by induction, because we know that a denumerable plus one element is still denumerable. So that means you can go by induction and show denumerable union of a finite set is also denumerable. And finally, if C is infinite, then that proof works, because now A and C are disjoint. Okay, any questions? Okay, here's kind of a big one here. I'm gonna leave this for you to ponder, because this goes further. A denumerable union of pairwise disjoint denumerable sets is denumerable. Pairwise disjoint. Denumerable sets is denumerable. So this goes one step further. Because what we had previously is if you have two denumerable sets in union, it's still denumerable. This means if you take a denumerable union, so in other words, if AI, so it's denumerable, all these bijective to the natural numbers. And there's countably many, or there's denumerable many things. And then look at the union. So now, if you take an infinite union of denumerable sets, as long as that infinite union is only denumerable in many, then it's still denumerable. Okay. Next, I'm going to prove this theorem to you. So think about how you would make this jump from just finitely many, union of finitely many denumerable sets to denumerable many. I'm gonna go through the details on this one here. Theorem. Subset. Of countable set. Remember, countable means either denumerable or finite is countable. This is probably not a huge surprise, right? I mean, a subset of a finite set is finite, right? And a subset of the natural, something, just take the natural numbers, for example. A subset of the natural numbers is either finite or it can be put in one-to-one correspondence with the natural numbers, it would seem. Suppose A is countable. And B is contained. So B is just some subset of this. If B is finite, we're done. Because after all, if B is finite, then any finite set is countable, and we have the conclusion. So we can assume B and hence A are infinite. Right, so we can assume that B is infinite, and of course, since it's contained in A has to be infinite too, because we know that any subset of a finite set is finite. So there is a bijection I've done my bijections in the other direction today for the most part, but for this proof, it'll be convenient to run in the other direction because bijections go both ways. It doesn't matter. So let F from A to N be our bijection. And notice F restricted to subset B is a bijection from B to F of B, which is the image. Numbers. So we now define a function from the natural numbers to F of B inductively. In the following way, we will let G of 1 be the smallest integer in F of B. And G of N, smallest integer in F of B, take away G of 1, G of 2, G of N minus 1. So in other words, G of 1 is the smallest integer in F of B, G of 2 is the second smallest, G of 3 is the third smallest, and we just go up the ladder like that. And notice that this set is never empty because we're assuming that B is infinite, and so F of B must be infinite too. note that if G of N equals G of M, then it must be the case that N equals M by the construction of G. And if C is in F of B, then C is in the natural numbers, and so is K in the natural numbers such that G of K is C. Because there can be at most C minus one numbers less than C. And so eventually it must get there. So this shows the natural numbers are in one-to-one correspondence with F of B. And this is in one-to-one correspondence with B because the first F is a bijection on that. Okay, that's a good place for us to quit for today. Any questions on this? Okay, well, I will see you folks on Saturday.